In the deepest basements of physics laboratories, far below the noise of traffic and the rhythm of ordinary life, there is a different kind of world. A world where temperatures are colder than outer space, where particles behave like ghosts, where reality itself seems uncertain. This is where the story begins, not with an explosion, not with a flash of light, but with a question that had haunted physicists for decades. What if there exists a state of matter we have never seen before, not because it is rare, but because we never knew how to look for it? For more than a century, quantum physics had been rewriting the rules of nature. Electrons were not tiny balls, they were waves, and sometimes particles, and sometimes something in between. Physicists learned to classify matter into phases: solid, liquid, gas, plasma. Later, they discovered stranger phases: superconductors, superfluids, topological insulators. Each new phase unlocked new technologies: transistors, lasers, magnetic resonance imaging, quantum computers. But despite all this progress, there remained a vast, uncharted territory in the map of quantum matter, a region known as quantum criticality. This is the borderland between two phases of matter, a fragile point where a system is neither one thing nor the other. At this boundary, electrons fluctuate violently, time slows down, energy scales disappear. Physicists called it a place of maximum instability and maximum possibility. But there was another frontier, just as mysterious. A different idea, born from pure mathematics: topology. Topology is the study of shapes that cannot be changed without tearing. A donut and a coffee cup are the same shape in topology. A sphere is different, and once you change the number of holes, the object belongs to a new class forever. In quantum physics, topology meant something revolutionary. Certain electronic states were protected. They could survive disorder, survive impurities, survive noise. They were stable in a chaotic world, and these topological states became the foundation of future technologies: fault-tolerant quantum computers, ultra-precise sensors, energy-efficient electronics. For decades, physicists believed something fundamental: quantum criticality and topology belonged to different worlds. Criticality came from strong interactions. Topology came from weak interactions. They should not mix, they should not coexist. And yet, somewhere in the equations, a contradiction was hiding. In a quiet office, surrounded by chalkboards filled with symbols, a group of theorists began to suspect something unusual. What if strong interactions could also produce topology? What if the most chaotic region of quantum matter, the quantum critical point, could also host the most stable topological structures? It sounded almost paradoxical. Criticality is about instability. Topology is about stability. How could both exist at the same time? For years, the idea remained a mathematical curiosity. No experiment had ever seen such a state. No material was known to host it. No measurement technique could clearly detect it. But physics has a long history of ideas that wait patiently until the right tools arrive. The breakthrough began not with theory but with a strange material: a heavy fermion compound. In these materials, electrons behave as if they are hundreds of times heavier than normal. They move slowly, they interact strongly, they form complex quantum liquids. Heavy fermion systems are famous for living near quantum critical points. They are laboratories of extreme quantum behavior. One such material had puzzled researchers for years. Its electrical resistance behaved oddly. Its heat capacity showed unexplained anomalies. Its magnetic response refused to fit existing models. At first, these were dismissed as experimental noise. But one researcher noticed a pattern. As the system was tuned closer to its quantum critical point, new electronic states began to appear. Not random, not chaotic, structured, robust, topological. To prove it, the team needed to see something that cannot be seen directly: the topology of an electronic wave function. This required a combination of techniques: ultra-low temperature measurements, high-precision spectroscopy, magnetic field tuning, and theoretical modeling that could interpret subtle signals. Every experiment took weeks. Every dataset contained thousands of points. Every anomaly had to be checked, rechecked, and doubted. Was it an artifact? Was it noise? Was it a known phase disguised as something new? Months passed, then years, and slowly a picture emerged. At the quantum critical point, the electrons did not simply fluctuate. They reorganized. They formed a new phase of matter, a phase where strong interactions drive quantum criticality, and at the same time, the electronic structure becomes topologically protected. This was not supposed to happen, and yet, it was happening. The researchers gave it a name: a topological quantum critical state, a state that merges two of the deepest ideas in modern physics. In this state, electrons are maximally entangled. Energy scales vanish. Fluctuations exist at all lengths and times. But despite this chaos, certain electronic pathways are protected. They cannot easily scatter. They cannot easily decay. They are immune to small imperfections. It is a phase that is both extremely sensitive and extraordinarily robust. A rare combination, a paradox resolved by nature itself. At first glance, this may seem like an abstract triumph, another exotic phase in a long list of quantum curiosities, but history teaches us something important. Every major technology of the modern world came from understanding new phases of matter. Semiconductors came from band theory, lasers came from quantum coherence, MRI came from nuclear spin physics, quantum computers will come from topological protection, and this new state offers something unique. It combines the enhanced entanglement of quantum criticality with the stability of topological states. This means future devices could be more sensitive, more stable, more resistant to noise, more scalable. Imagine quantum sensors that detect gravitational waves with unprecedented precision, quantum computers whose qubits are naturally protected from errors, electronics that operate with almost no energy loss, materials whose properties can be tuned on demand. But there is more. This discovery does something even deeper. It rewrites a rule. For decades, physicists believed that topology requires weak interactions. This work shows strong interactions can also create topology, which means the space of possible quantum materials is far larger than anyone imagined. After the discovery, theorists began to redraw the phase diagrams of quantum systems. Entire new regions appeared, new transitions, new phases, new critical points. The border between chaos and order was no longer a line. It was a landscape, and hidden within that landscape were likely many more unknown states, waiting. Of course, this is only the beginning. The state was observed in a specific heavy fermion material, at extreme conditions, at temperatures near absolute zero. To turn this into technology, researchers must find more materials that host this phase, learn how to stabilize it at higher temperatures, learn how to control it with electric fields, pressure, and light, learn how to integrate it into devices. This will take years, perhaps decades, but that has always been the rhythm of physics. Discovery first, understanding next, technology last. There is something poetic about this discovery. At the point where matter is most unstable, at the edge between phases, at the brink of collapse, nature creates something new, something structured, something protected, something powerful. A reminder that the deepest order often hides inside chaos, and that even in the most uncertain regions of reality, there are still secrets waiting to be found. The next quantum revolution may not come from building bigger machines, but from discovering new states of matter hiding at the very edge of reality itself.